In her book, Interdisciplinary Curriculum, Design and Implementation, professional curriculum expert Heidi Jacobs described a cross-curricular or interdisciplinary approach to teaching as applying knowledge, principles and skills to more than one discipline simultaneously. In 1991, educational researcher Robert Mazzano and Professor of Education at Harvard David Perkins went on to say that it is useful in developing thinking and reasoning and supporting teachers to try and make the curriculum more relevant to children by applying a context to what they are teaching. Really what cross-curricular teaching is supposed to do is get two or more subjects out of their separate boxes and working together to extend pupil understanding and develop problem-solving and independent study skills by applying learning to a variety of different contexts. There has been some contention on the value of cross-curricular teaching in comparison to the more traditional discrete subject method. The Three Wise Men report by Alexander, Rose and Woodhead in 1992 criticised poorly planned topic work that resulted in a superficial learning experience or poor understanding. It is often used to argue for discrete subject teaching. However, it is frequently overlooked that the report did acknowledge that when done correctly and well planned, topic-based learning could produce a high standard of work. Criticisms of cross-curricular teaching include the potential for the value of topic-based learning to be watered down by excessive linking of subjects to a topic. It is critical to ensure that links between the subjects are valuable so that the skills of each subject are explored to an adequate standard and the areas of the curriculum are not just included in a theme for the sake of continuity. In addition to this, assessment of cross-curricular topic work can be more difficult because there are often several learning objectives and there can be great potential for learning, making assessment unfocused. This can be overcome, however, if due care is paid during the planning process to know exactly how each subject within the theme topic will be assessed and keeping it focused. On the more positive side of things, it has been said that cross-curricular work can offer great opportunities for assessing skills such as problem solving as well as research and independent study. Maths is applied in many areas and in a vast array of contexts, from money and economics to mathematical biology and computer science. Almost all subjects in the school curriculum have some links to mathematics. However, maths and science seem to have a special connection. In 2010, Marcus de Sautoy, Professor of Mathematics at Oxford University and the person responsible for communicating science to the public on the university's behalf, said that mathematics is the main driving force behind scientific discovery. This discussion is going to focus on the special relationship of maths and science and how integrating them differs from interdisciplinary teaching of other subjects. In Math Skills for Science, Louise Pathram explains how for children to be effective learners they need to develop their mathematical and scientific skills in parallel. She also states that almost every scientific investigation or experiment is likely to require one or more mathematical skills, such as classification, counting, and many more. One way in which the argument is made for integration is in the idea that both subjects lend well to an inquiry, problem-solving, and investigative approach to teaching and learning. In addition to this, it is hard to argue against the idea that science requires mathematics to model its ideas and that math benefits from a scientific context. Integrating maths and science does not always have to begin with a scientific investigation which is then solved mathematically. Truly integrated instruction may begin with a problem scenario posed in either subject, pass through either subject in the investigatory phases and find a resolution in either subject. Another argument for the integration of maths and science is in the way that the two fields are learnt. According to a 4-person team from California University, mathematics and science are best learned interconnectedly, and integrated curricula enhance student motivation. The investigative article leads to the argument that both subjects are learned in the same way. This is developed through the investigation of learning processes associated with both subject matter areas. Using the 5 process standards of learning mathematics and the 5 E's of scientific inquiry from the National Research Council, the article builds a case for the learning of both subjects being learned in very similar ways. The 5 E's of science relate to how science can be learned, as these are considered the parts that a science lesson should progress through. The article went on to present a visual representation of how the 5 processes of mathematics and the 5 E's of scientific inquiry are linked, which I have given a brief demonstration of, just to show how interlinked these two sets are in the article. This representation has, however, been simplified from the original. The constructivist teaching philosophy also supports an integrated approach. Constructivists contend that students learn through connections formed between prior knowledge and new experiences, and as connections arise among existing ideas. This notion is accentuated by brain research that supports thematic teaching, and the idea that all people process information in a more comprehensible way through patterns and connections than fragmented pieces. This is further supported in Haylock's Mathematics Explained to Primary Teachers, which states that being a successful learner of mathematics involves constructing, understanding, through exploration, problem-solving, discussion and experience. Considering these ideas, I am going to look in more depth at a specific area of maths and see how it also applies to science and how the concepts from both overlap. Classification is present in both mathematics and science and is integral to the understanding of both. As such, I have chosen this to be my focus. When I say classification, I am referring to the process of separating objects, concepts, symbols, or anything else into categories using the similarities and differences between it and similar things. Haylock's Mathematics Explained for Primary Teachers says in regards to classification that recognizing similarities and differences are fundamental cognitive processes through which we organize and make sense of all of our experiences. Classification is present in just about every aspect of maths. Numbers can be classified as square numbers, whole numbers, odd numbers, even numbers, factors, negatives, and so on. It's perhaps most evident, however, as part of shape. Shapes can be classified as two-dimensional, three-dimensional, rectangles, spheres, triangles, and so on. And these can often further be subcategorized into other categories, such as isosceles triangles, scalene triangles, and right-angle triangles. Classification is also a big part of science. Children in primary schools are asked to sort animals into categories like herbivores, carnivores, and omnivores. It is an essential skill in understanding habitats and the complex ecosystem that we live within. It is also apparent in plant science to understand the vast quantity of species that are often categorized by their reproductive cycles. As already stated in Louise Patherum's book, Math Skills for Science, she claims that most scientific investigations will require the use of classification. By integrating the teaching of classification skills for maths and science together in a series of lessons, children may develop a greater understanding of how to identify and categorize things by their similarities and differences. This may or may not include the use of Venn and Carroll diagrams or branching databases as a visual representation. During my teaching practices so far, I have noticed a great deal of misconception in the understanding of both shapes and the classification of living things and animals as part of my university research project. The teaching of classification in a variety of contexts may help to further this understanding and address some of these misconceptions. Using Louise Patherum's Math Skills for Science and Robinson's Interdisciplinary Planning and Instruction handout as a guide, I considered how a series of integrated lessons might look. At first, the children would sort sets by one criteria that they decided upon, and then reflect on this at the end, beginning with physical objects for a more tactile learning experience. Following this, the children would sort them using Venn diagrams and branching databases to learn to represent this categorization. Afterwards, the children would be involved in choosing two criteria and labeling the groups for themselves. Finally, to further the understanding, the children could be asked to create their own sets to categorize. Leading on from this, the teacher would ask them to check for their understanding of what various concepts mean, through questions like, what is an equilateral triangle like? The lessons could be differentiated by only using one criteria for the lower ability children in the group and the higher ability children solving higher order problems. The understanding of mathematics and science, both logical, problem-orientated strains of thinking, lend themselves well to computers and technology. For developing the understanding of shape, for example, there are a large variety of resources available online that teachers and children can use. As part of the Maths Teaching Pedagogy module at BCU, students were shown one particular such resource called Virtual Pinboard from Crickweb. It allows children to control a variety of parameters of shapes in ways that are much more practical than with other resources. This resource is especially useful in showing children how irregular shapes look, like a pentagon that doesn't have equal length sides and angles. The new curriculum for ICT includes the requirement for children to begin learning programming in the primary years. In constructivist theory, there is the idea that children learn best when engaged in the production of some tangible artifact and engage in discussion and feedback with teachers and peers. One way that teachers could support this is with a solid understanding of Scratch, an internet-based scripting system that can be used to teach computer programming concepts and skills. In line with this theory, it may be beneficial to support learners in classification through having children develop their own program where they classify. It's worth noting that there are some difficulties with integration, mostly in terms of how best to implement it. There has been some research into integrating the subjects being taught during teacher training, and was showing mostly positive results. However, another article argued that continual professional development was the best approach to integration. In-service teachers have the experience and skills to monitor the impact of their practice on pupils' learning. Whichever method is used, it is clear that the integrating for maths and science needs further investigation and to be taken seriously if children are going to be adequately prepared for the highly technological modern world.